Hello guys, can you hear me?
Yes, sir.
Yes.
Okay.
Yes, sir.
Yes.
Okay. Yeah, I don't know what happened to my Microsoft Teams. I think this team got deleted. I mean, I don't know how it happened. But just now when I was trying to log in, I found that it is deleted. I mean, the earlier team is not there in the list.
Sir, it must be hidden because we can access the team, so it cannot be deleted.
Sir, it is
Oh,
visible for us.
Yes, sir. So it
but
must
I
be
cannot see it.
hidden.
Do you know, oh, I cannot see it, but do you know any other way how to get back that team? Because I shared everything there, so I don't know how to find it.
Sir, in hidden channels.
Okay, maybe I. Okay, maybe I'll I'll give it a try later on. And if there is any change of schedule, I will let you know. Changes teams, I'll let you know. But let us start today because we have to finish some topics. This is important for the exam. So yeah, so yeah, okay. So yesterday we talked about expected value. Okay, or in fact, in general, we define what is called moments about origin. Okay, so this is what is called the mean, and here this is where we define what is called moment, right? So yeah, in fact, I must tell you this all these terms like mass function. So that term, the mass, the word mass, or when we are calling it a density function, the word density, and when you are calling it a moment, okay. So these all these terms are related to physics. In fact, a long time back, when people think about experiment, they always think about physical experiment, right? So when you conduct a physical experiment, like in physics, okay, so you have to repeat the process, okay, to get a final answer. Right? Oh, so you have to repeat the experiment because every time you would not get the same answer, okay, whatever you are measuring or doing something, okay. So you have to perform an experiment for many number of times, and then finally you conclude that what is the possible answer. And for example, this moment, this is related to moment of inertia, and so if you look at moment of inertia, you will see that suppose something is rotating, some object is rotating around some axis, let's say the x-axis, then depending on the different points of that object, you can consider the mass around that point, and let's say the distance from the origin, okay, when it is rotating around this axis, okay. So and then you can compute this moment of inertia using like square of the distance, or x is the distance times the mass, so which is fx actually, because this mass is here defined in terms of probability now. So and then you take a sum. So that's how. So this is a second order moment. Okay. So this is what is called the second order moment here in our definition. If you take n to be 2, so if you take n to be 2, so this is what it gives you. This is moment. So the second order moment. So yeah, so all these terms actually they came from physics. Okay. So yeah, because by experiment we call it physical experiment. And then we talked about, okay, then we introduced a concept of what is called expectation, EX, which is nothing but the first order moment, or just first moment, okay, which was like sum over x of x, and then sum of, sorry, integration. Okay, so here it is discrete, this is a range space, and then otherwise it is minus to infinity, x of x dx, okay. So this f is nothing but the probability mass function here, and this is the probability density function here. So, but here it is probability of x equal to x corresponding to the random variable, but here it is not. Okay, because the way we defined it, so the way we defined this PDF or the PMF, okay, they are different in the for discrete random variable and for continuous random variable. So let me just ask you a question so you'll understand what it means actually. So we tried to justify what it is, and we discussed that it is some average values of something. Okay, So, for example, let me ask you a question, and let me discuss this a little bit. Suppose I ask you, what is your expected grade in this course? Okay, so how do you answer this question? What is your, I mean, what grade you can expect from this course? Okay, the expected grade. So how do you answer this question? Now, if I if I want to answer this question, I have to first consider the sample point, the sample space and everything, because everything I know about this experiment. Okay, so I can consider sample space, which is like all the grades possibly. So let's say it is EX, A, B, what C, D, and let's say P. These are, let's say, the grades. Okay, let us forget about the F grade. So we have this, I mean, 6 grades. Okay. Okay, so okay, so the thing is now then I have to define, because I cannot compute the expectation. Okay, what is my expected grade? So somehow if we want to apply our techniques, whatever we have learned, then what I have to do first is that, like, okay, I have this sample space, which is a discrete set. Okay, I have 6 elements here, EX, A, and so on, let's say up to P. And then I have to define a random variable here, X. Okay, and so I have to associate these grades, okay, with some numbers, because they are not associated with numbers. So I cannot perform any kind of summation of addition or multiplication. I cannot do that. So let us do it in a standard way. So let's say expect the EX grade is associated with 10 marks or something, 10 points, whatever it is. So it is with number 10. A is, let's say, with number 8. So this is the random variable here actually. And this is 6, and this is 4. Okay, so this is A, then B, then C, then D, and then P. Okay, 2, 0, whatever you want to write. Or you can write 10, and then 9, okay, then 8, then 7, then 6. Okay, and for P you can write 5. Okay, anyway you can define it. This random variable you can of course define. Now the question is, I have to assign now probability of getting 10. That means probability of getting EX. Okay, somehow I have to define it. Then only I can compute its expected value. So now it can be done in many ways. So this is actually the data you have. Now what is the data here? The data is like the historical data. So I can consider the data to be equal to all possible grades in all possible courses you attended here at IIT Kharagpur. So then I can consider like how many EX you got in how many courses, and that way I can have a notion of probability for EX, let's say. Okay, EX. So let's say it is something. Okay, so suppose you have considered n number, so you have attended or registered n number of courses, and let's say you got k1 number of EX in all those courses as a total, then you can define k1 by n. Similarly, you can define probability of E, or let's say A, to be equal to k2 by n, and so on. This way you can define some probability, and then you can compute the sum like x times px. So these are the xi's here. So let's say this is my x1, this is my x2, this is my x3, this is my x4, x5, and xx. So then you can compute the sum xi and then p of xi. Okay, p of xi, or just p of x equal to xi. So then I equal to, let's say, 1 to whatever, 1 to 6. Okay, then you will get a value. You'll get a number. And then this number need not be the integers like 10, 9, 8, 7, 6, 5. This need not be the integers, one of these integers. So it will be some number. Let's say 7.2, or let's say it is 8.9, or whatever it is. You will get some number. And then you can probably think about, okay, the expected. So suppose you get some number like 8.5, then you may get, let's say, 9, something close to A grade or close to B grade, something like that you will get. Okay, so everything depends on, so your analysis here depends on how do you define this probability. Okay, and of course, how do you define these numbers? And so the way you define the numbers, you'll get a value according to that. So here expectation means, so if I ask you what is your expected grade, it is equivalent to saying what is your expected point here. So the values you are assigning to all these grades. Okay, so then how, so if I give you any particular grade for a new entity, like for a new course, then your question will be, then the expected value will be like, okay, what is the kind of expected number of points you're supposed to get in this particular course? Okay, but of course, so you can change these probability values. For example, so this is one way to do it, but there are different ways to do it. So that's why whenever we deal with data, this is in your hand. So you have to define. So this may not be a correct way of representing the experiment. You may probably would like to do like, okay, so let us consider only those courses which are did from the maths department. So then your sample space is all it consists of only those courses which are offered from, let's say, the maths department. Then this n will change. N will change, K1 will change, K2 will change. Then you have another kind of a probability distribution, another kind of a probability mass function. And accordingly, you can calculate your expectation. You can again change your sample space. Let's say you consider all the courses which are offered from not your parent department, not your department, but outside your department. So it can be from physics, chemistry, maths, or from electrical engineering, whatever it is. So they consider all those courses and consider the grade. So then also the probability changes and you'll get a new expected value. So this expected value is based on those courses. This expected value is based on those courses and so on. Okay. So whenever you are doing kind of a data analysis, everything boils down to how do you define your probability mass function in this case when it is finite, or in general when you consider the probability density function. Okay, so that's how it is defined. And okay, okay, and then we talked about moments. Okay, moments. So if we just look at the definition of moment, let's say for a finite sample space, then what we did here is, let's say x1 plus x2 plus dot 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 xn. These are the, so let's say the rx is here is like x1 x2 dot 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 xn, and then if all are equally likely, let's say, then you divide. So this is just the average. Okay, this will give you the expected value. In fact, when it is large, so you have to take n goes to infinity, and then accordingly you will get your expected value. Now one can say, okay, why I am only considered about x1, x2, xn? Maybe some of them could be positive, negative. Okay, cancel out. Okay, so somehow you will get some number. Okay, that is okay, but I'm not interested about that. But I'm interested about the square of it and the sum and then divide it by n. So when I'm dividing it by n, here it means the probability, this is equally likely. That means I'm taking x times 1 by n. This is the probability here. Probability of occurrence of x1. Similarly, x2 square times 1 by n plus dot 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 plus xn square divided times 1 by n. This is my expected value. But somebody may be interested in talking about, okay, x3. I'll take the cube of this and then I'll take the average. Okay, so it gives you different means. Then this is like cube or square. Here it is square. Here it will be cube and so on. So if you take the nth power of all these numbers, then you'll definitely get these values. Okay. Okay, so this is one thing. Another thing is in terms of applications, let's say, sometimes what happens is the sample point itself are real numbers. For example, you are producing, so there is a company, let's say let's say it produces let's say bulbs, okay, different kind of bulbs. Now the company wants to calculate this average lifetime of a bulb, whatever it produces. Okay, then the same thing they have to consider, like different kinds of bulbs they have to consider, they have to test it, and they have to observe for a long they have to perform the experiment, repeated experiment, let's say for a long time, or let's say for a long sample, for considering different kinds of bulbs they produce, and then they come up with some value, okay, depending on what is its lifetime. Okay, so these are very realistic things, although sometimes it may not be a good idea when the sample space contains only, let's say, 2 or 3, or let's say very small number of points. Okay, for example, if somebody's salary is like, let's say 100 rupees, so there are two brothers, let's say. Okay, let's say the first brother, okay, so let's say his salary is, let's say, some 10k per month, and another one's, let's say, 100k per month. But if you take the average, okay, it will be more than, let's say, 50. It will be more than 50k. So if you just say the expected salary is 55 or 50, then it is never near to 10 or even near to 100k. So it means the average here in this sense is not a good idea. You need to find out something else. Okay, you need to find out some other means of measuring the same thing. Okay, so average sometimes gives you a good idea about what is your expected value, like the salary here. For example, here salary itself is a number. Okay, some amount of rupees, let's say, per month. So it is itself is a number. So you don't need to define another random variable. Of course, you want to, if you want to, for example, you want to consider the sample points as not just 10 but 10 cube and 100 cube, then you'll get a different value for the random variable. So then the random variable is like from x, if it goes like 10 cube, and here it is like 100 cube, or you want to take something else, some other random variable you want to consider, doesn't matter. So sometimes you need to define random variable and sometimes you don't need at all, okay, because you are satisfied with the sample points, which are already real numbers, let's say, then you can deal with it. Okay, otherwise, if you are in a situation where these are not real numbers or they are not meaningful numbers, then possibly you have to do it. Okay, and another thing I want to say is that whenever we define this, the moments, we said this is x to the power, okay, so I think I denoted like this, expected value of x to the power n. And then we also said this is called what is called the central moment. So it was like x to the power n, and then fx, and then here it is x to the power n fx dx. But you can define it with respect to some some other value. Okay, and how can you do that? So let's say you consider some number, let's say some number a, okay, which is a real number. Okay, then what can you do is like you take expectation of not x to the power n but x minus a to the power n. Okay, so then this will be central moment about the point a or the number a. So then the formula will change a little bit, and then this will be just sum over x minus a to the power n fx, and this will be of course a similar thing. So x minus a to the power n fx dx. So this is then this is the moment about or you can say central moment about the number a. Okay, so it is just a similar concept. Okay, you are just changing your origin. Okay, in fact, expectation can also be thought of as the center of mass for an object, because we are doing the same thing here. Okay, so from the physics students, I mean, if you have done physics courses, then this is the same way that you calculate also center of mass. Okay, now I also said, okay, these moments need not exist at all. For example, let me give you an example. Let's say the Cauchy random variable, random variable with some parameter, let's say theta. Okay, so which we had computed. I think it was 1 by, so the PDF was 1 by 1 by pi, and then it was 1 plus x minus theta whole square. So this is the PDF of this random variable. And now suppose you want to compute its let's say expected value. Okay, expected value. So then what can you get? What is the expected value? That means you have to compute x fx dx. Okay, from minus infinity to infinity. And you'll see that this does not exist. Okay, this will be infinity. This does not exist. In that sense, we'll say it does not exist. Okay, why does it not exist? Okay, so there is a theorem in calculus. I think if you remember it. So this is, if this is finite, means if it is less than infinity, then this is also finite. X fx. So mod of it, the positive values of this or non-negative values of it. Okay, that if this is the integral here, the function gx, let's say, we take the mod of it, so it is actually less equal to this guy. So if it is convergent, so then you will see that this value, okay, will also be finite. If this is finite, then this is also finite. Now for this Cauchy random variable, if you compute this minus infinity to infinity and mod of x fx dx, then you'll see, just a minute guys, I have to take this. সুন্দর বলছি আজ একটা লাঞ্চ দিয়ে দেও না, না মাছ দিয়ে দিও তুমি, ওই থালি বলে না যেটা, থালি দাও যেটা, ওটা দিয়ে, হ্যাঁ দিয়ে দিও, হ্যাঁ ঠিক আছে। Okay, so so if you just compute this, then you will see this will be infinity, and this expected value for this random variable, it does not exist. Okay, in fact, you can also show here that for the Cauchy random variable, it is this moments, any nth order moment or any nth moment. Okay, this does not exist. Does not exist. If it exists, you get a clue about this doesn't exist for any n, for any natural number n. Okay, so if it exists, then you will get a clue about how this random variable, the values, how these values, the xi's, okay, or fx, how the values fx for different x, how these are distributed. Okay. Now, so another thing can happen. Suppose you have a data, okay, set of data, and let's say you have different kinds of data. So let's say here it is time. So you are measuring something which is based on time. Okay. So let's say you are measuring temperature. You want to calculate the average temperature during the month of, let's say, July or August. Okay, you want to calculate that. So start taking different measurements at different time of points. Let's say you have measurement like, let's say in the previous year, this year you are doing the measurement. So you have taken, let's say, T1, T2, maybe the 1st August, 2nd August, 3rd August, and so on. You are getting some values. Okay, there could be some values which are almost same. There will be a difference sometimes because of the weather and so on. Okay, then these are these values. Let's say this is x1. So this is x1, this is x2. Okay, so these are those values, x1, x2, xn. These are already real numbers. Let's say, so whatever the unit is, doesn't matter. According to that unit, let's say these are the values.
Hello, sir.
Now,
hello, sir.
Yes, yes.
Sir, I think the theorem that you stated above, it just like I'm thinking like it is just opposite of it, like the about the calculus, sir. The integration of minus infinity to infinity. Yes, sir. If the modulus thing is less than infinity.
Yeah. If it exists, then it exists. Okay. So, okay, here, okay, I should remove this down. If this exists, then yeah. If this is less equal to this, so if this exists, then this exists. Yeah. What is that? I think the theorem was okay. So if you have fx integration fx dx, then integration of less equal to fx is less equal to mod of fx, right? Right. So if this converges, absolutely, okay. So I think I should write it like this. If this, then this. Yeah, you're right. So if then, because it is less equal to this, so if this is finite, then this will also be finite. But even this does not exist, so there is no point that this will exist. Yeah, you are right. You are right. You are right. I missed that. Yeah. Okay. So now, what I was saying. Yeah. So for different values of t, you'll have this measurement. Let's say x1, x2, and so on. Okay. This is your sample. This is your sample space. S is like this.
Sir.
But
hello, sir.
Yes.
Sir, then it will create a problem like if like sir in this case this is less than infinity, that the modulus thing is like approaching to infinity. So but we can't say that this fx and the simple x fx will also approach to infinity, like the converse is not true.
No. What I'm saying is, okay. So let's say what I'm saying here is, suppose this is an integral value, okay, and this is an integral value, okay. Now this exists. This is the original one, this I1. Okay. So the theorem is, if this exists, okay, this converges absolutely, meaning if the modulus value converges, absolutely converges absolutely. So this is called absolute convergence. Then, okay, I would say, okay, let me write it here. Let me write it here. What I'm trying to tell you is the following. If this mod of fx dx is finite, if this converges, then this converges. This is what I wanted to tell. Because
Yes, sir.
yeah,
Yes, sir. I agree with this. But
yeah,
like as per the question that we are doing.
yeah. I'm coming back to that. So let's say, so this is, let's say, converges. Let's say this is I1, this is I2, then I1 less than I2. So if this is finite, then this is also finite. Now what I'm saying is, this does not converge. I'm showing that this does not converge, then obviously this does not converge. Because if this converges, then this converges. But I'm showing that this does not converge. This is infinite. So then this does not converge. This is what I'm trying to say. Because if this converges, then this converges. Means if this is finite, this mod finite, then this is I1 is also finite. But since this mod, like if this I2, this does not converge, this is not finite, then of course this is not finite. So this does not converge. Is that okay now?
Like, sir, it can be like if I2 does not, if I2 does not, like if I2 does not converge, then is it necessary like I1 will also be not converge?
Yes, yes. Because if this converges, then all of this will converge. But I'm saying that this does not converge. Is there any confusion what I'm saying? If this converges,
No, sir, I am agree with you what you says.
yeah.
Like in the converse part that if I2 does not converge,
Oh,
then
yeah,
sir,
if that's that. Oh, okay. So you are asking, okay. So, okay. If this integral converges absolutely, yeah. So absolute convergence implies convergence. But if absolute does not converge, okay, then how can you say that this will converge or not? So my theorem should be then, if I remember it correctly, that this is always physical to this.
but sir,
So
like in this case, both absolute and the like I2 and I1 are likely to be same, like because it is squaring. So I think
yeah, what is that?
yes, like in this case, I1 and I2 like to be same because like in fx we have square. So I
We're
think
not, no, we're not in square of it. Oh, the f, no, but x is here. No, x can be anything. X can be negative also. X can be
oh
negative
yes,
also.
yes.
Yeah. So what I'm saying here is absolute convergence meaning converges. So, or if this converges, then this converges. Okay, maybe we'll get back to you later. We are running out of time. Okay, I'll think about this. Okay, I'm a little bit confused right now, so maybe I'll get back to you this example later on. Okay, but you can find out that this will not converge, so I'll get back here. Yes, I don't want to
Okay, sir.
waste time, right? Yeah. So now what I was saying here, I forgot what I was saying. Yeah. So the temperature. I need to say something. So anyway, so yeah, so whenever you have, okay, let's say you have t, and you have this different values. Okay, let's say x1, x2, x3. Okay, these are the different values depending on time. So basically, your sample space here, let's say x1, x2, and some number of times you have measured this. So you have performed this experiment. Okay, maybe you have measured this temperature, let's say, for some number of time. And then of course you will get some value, okay, for the mean, let's say, or for the expected value. You will get some value for the expected value, because you know, so for example, probability of some x1, probability of x2, probability of xn, you know this due to something, a previous experiment or whatever it is. And these are the values which are given to you. From there, you can find out the experiment, the expectation. So now what can happen is, suppose you the question is, can you modify the data a little bit so that you will get a desired expected value? Meaning, suppose I am asking the reverse question: what could be the possible changes in the temperature so that the expected temperature will be, let's say, 35 degrees centigrade in the month of September. Okay, what are the possible changes? So I'm asking you the reverse question. And I have measured, measured like this is like x1, x2, something like that. But I want to somehow change this. I want to change my mean, my expectation, or something I want to do with this data such that I will get my desired mean. Or maybe I'm interested to not about these exact values, but a variant of this x1, x2, because suppose somehow I do not know whether these values are measured precisely or not, meaning there can be some kind of an error, some plus minus of error. Okay, so because we do not have the right equipment, right apparatus or right equipment to measure this, so there is a chance of some amount of error. So instead of these values, in fact, I should consider some values like this: xi plus some epsilon I, or let's say some ai. Okay, some AI. Now, let's say AI is maybe due to the problem in the let's say apparatus. Okay, or the equipment which you are using, there is a noise, and then I need to measure this. In fact, I need to perform this measurement. Okay, and I need to calculate the average based on these values, not based on these values. So I can tweak that. So the question is in general. So this is the idea. This can be stated as a theorem, that suppose I have a random variable x with let's say PDF fx, and let's say I have two numbers, let's say a and b, they are just real numbers. Then the question is, what is the expected value of a times x plus b? Okay, so this is what. So meaning, if I change these values to here, okay, xi is to xi plus a, let's say, or you can add here some number, let's say xi. You add a constant value, not you add a constant value. The noise is constant, but also you are interested to measure, let's say, some a. Okay, a times xi plus b, some scaling and then adding. Okay, basically what you are doing is, earlier whatever the numbers you had, if they are on the y-axis, okay, it is not exact resemble of this, but so basically whatever you had these numbers, you are changing the line. So this is now a line. So like y equal to mx plus c. This is your new value, yi. So you are changing the sample point. So making from xi, you are giving a transformation, which is a xi plus b. You are getting a new sample. You are creating a new sample. So let's say x hat, which is like a x1 plus b, a x2 plus b, and so on. Okay. So then the question is, can I compute its expected value for this particular sample space or this particular random variable? Okay, using the expected value of the previous one. And it can be proved that it will be nothing but a times ex plus b. So here, what is happening here is, this is a standard notation, but it has a meaning. This is a function. Here it is a scalar, but the meaning here is, there is again a function which is identity function here multiplied with b, or the meaning of this is nothing but a times xi, the value of x, whatever the value of the values x is taking, so that plus this number. Okay. So that is how you can prove that the expected value of this new random variable, okay, will be a times cx plus b. You can just prove it quite easily for the case of continuous random variable. If this is the case, then we have minus infinity to infinity. Okay, it is very simple. Plus b fx dx, and then you can just manipulate this, take out all these sums, and then you can prove that it is nothing but this ex plus b. So this is just a formula. Now we'll introduce one more measure, which measures the spread of the distribution. So how much spread this is. So mu will give you some value. So let's say these are x1, x2, xc, or if it is continuous, okay, it is something like this. Let's say this is a non-zero portion of the PDF xa. Okay, then I want to find some like this mean, which is somewhere here. Okay, somewhere here, let's say. And then how much spreaded this is, okay. So for that we have a measure which is called the variance. Okay, so variance measures variance, which measures the spread. Measures the spread of the distribution or the PDF, okay, of the distribution F. Okay. So what is the formula here? This is the definition. The formula here is variance of X is defined as expected value of X minus EX. EX is the mean, okay, and it's whole square. So basically, this is nothing but, we talked about moments about a point. So here, moments about a point meaning what? This one is the moments about this point A. Okay, nth moment, okay, nth moment about the point A. So here, same thing is happening. This is actually the second moment. This is actually the second moment. Second moment of X about the mean. And first moment will of course be 0. So first moment is this, instead of this 2, it will be 1. First moment, okay, about the mean would be equal to 0. And second moment is known as the variation. And this variation is also denoted as sigma square X. Okay, this is the variance. And so this is a value which is positive, and you can show why it is positive, by the way. I will show maybe a little later. And then this positive square root of this, positive square root of sigma square, which can be written as, or can be denoted as let's say sigma X, which is plus square root of sigma square. Then we'll say like this is what is called the standard deviation. This also measures the spread. Okay, so standard deviation. Deviation. Okay. And in fact, you can prove, the question is how to compute this variance. So you can prove that sigma square is equal to E of X square. So it's the second moment about the origin minus the square of the mean. Okay, you can prove that square of the mean. The proof is also very, very simple. Okay, so use the definition that this square is nothing but this of X minus, let's say mu. Let me write it at mu or mu X. Okay, the square of it. So then if you take the square of it, okay, like X square plus or minus 2 mu X plus mu X square. And then this will be, expectation is kind of, so this is like Y, this is a new random variable, right? Square of this original random variable X. This is again a new random variable, the entire thing. It's a new random variable. This is again a new random variable. The random variable here is the identity function, the scaling of the identity. Okay, it's a random variable. So we can show that this can again be written as, using the definition, this minus 2 mu X and EX plus mu square, and yeah, and then this will be EX. So here EX equal to mu X again. So this will be 2 mu X square. So it will be EX square minus mu X square. So this is the formula how you can compute. But again, the question, so this is the formula for computing for variance of the random variable. So for variance, the computation of variance, what you have to do is you have to compute the E of X square, expected value of the random variable X square, or you can say a second moment of X about the origin, and you have to subtract that with square of the mean. So that will give you the variance. And again, the same question one can ask, which is, okay, if I change my random variable, let's say X was my random variable earlier, now I change it to this, then what is the change of the variance here? And again, it can be shown that it does not depend on B, but the spread of this new only depends on A, how you scale it. So this is A times variance of X, which is like using the definition, you can just prove it. So I'm not proving it right now, but you can prove it like you just apply the formula and then. So I mean, what are the use of these formulas? Let me give you an example. Let's say I have a random variable X with mean mu, and let's say variance is sigma square, which is positive. And now suppose my question is, find values of A and B such that the mean of a mean of, let's say, ax plus b is 0, okay, and the variance of x plus b is 1. Okay, so then basically what you have to solve is, okay, 0 has to be expectation of a plus bx, then you can use the formula. So this will be a plus b times mu, or mu x, it is equal to 0. Similarly, for the variance also, you can write 1 should be equal to the variance of a plus bx, then which is, you can find it b square sigma square or sigma x. Now you know the variance, let's say mu, and you know variance sigma x, then you can find the values of a and b. Okay, so that way you can compute for what values of a, b. So how do you scale and add the original random variable such that your new random variable will have a desired mean and a desired variance? This will come back, this fact, when we'll talk about normal random variable. You'll see there are two concepts there. One is a normal distribution, another one is standard normal distribution. So the difference is standard normal, meaning we always consider 0 to be the mean and 1 as the variance. Okay, so variance means how much spread it is, how much spread it is. We'll talk about it. So you can always give a transformation to your random variable to get a desired mean and variance, and this is the way to do it. Like if you have random variable x, then you can choose a and b to have a desired mean and a variance. Now we'll talk about the famous Chebyshev's inequality. Chebyshev's inequality. Chebyshev inequality. So now say here, when I say that standard deviation, or let's say the variance, they measure the spread of a random variable, what does it mean? So let's say I have a distribution, something like this, something like, let's say this one. This is actually called a normal distribution, but we'll talk about it later on. Let's say I have distribution which is PDF like this. This is my fx, which is the PDF. Okay, so I have a random variable whose PDF is this, and let's say this is the origin. So its mean is, let's say, the origin, something like that. Okay, so mean meaning in the, okay, so we talked about it. So here, this is the, let's say, the PDF, the density function. Now, how much spread it means how much, what is the length of this? Okay, for which, let's say, it will be approximately 2. It is approximately, let's say, 1. Let's say it will be actually, if you draw it, let's say it will be very close to 0 when it is 3. Okay, same thing is happening here. Let's say it is symmetric about the origin, so it is 1. Okay, it is 2 here, and it will go to 0. Okay, when you take, let's say, 3. So I want to measure how much spread this PDF is. Okay, but then this spread, okay, how much spread it is, okay, that should influence the area under the curve as well. Meaning, if I consider the spread only this part, so this is variance 1, let's say. Okay, then I'll say, or let's say variance 2. Okay, then I'll say, okay, this will consider some amount of area. When I consider the spread to be equal to only this much. If I consider the spread to be equal to this up to this one, then I have this entire area here under this curve. So that means what is happening here is, if you so this value, the standard deviation, or let's say the variance, that also controls the, depending on what value you are taking, that also controls the area under this particular curve, which is fx, this particular PDF. Okay, now here this mean, let's say, is equal to 0, and then my general question would be, if I take the spread to be equal to mu plus something, mu plus, let's say, 2 sigma from mu minus 2 sigma. So in this particular interval, if I take this, okay, what is the area under this curve? So that means here, if I have a corresponding, let's say, curve like this, let's say here PDF, let's say here, and this is, let's say, mu. So I take some mu, suppose up to here, mu plus 2 sigma, and mu minus 2 sigma. Sigma is the standard deviation, let's say. Then my question is how much area? Why the area is important? Because how much mass, how much probability is already gone or already occupied in this entire space, which is under this curve. Okay, that can be computed. I can make a guess. Okay, so this value then, in general, let's say if I replace this by something like mu minus some k sigma to mu plus some k sigma, okay, some values of k in this x-axis, okay, in this x-axis, suppose here mu, it need not be origin, but some mu, and here I have some k value of k for which it is mu minus k sigma and it is mu plus k sigma, and I want to see, okay, how much area it can occupy under this thing. So this is let's say the PDF, then how much is the area? I want to make an estimate about this. And Chebyshev's inequality solves this problem. So this is the theorem, statement of the theorem, which I am not going to prove. The proof is long. You can find it in any book. But so let's say the statement is the following. Okay, let x be a random variable, x be a random variable with the PDF fx. And now let us say if mu and sigma denote they are the mean and the standard deviation of x, then the theorem says probability of mod of x minus mu less than k sigma, this will be bigger or equal to 1 minus 1 by k square. So what does it mean? What is the meaning of this statement? So here if you expand it, so what is here? So here it means x is lying between mu minus k sigma to mu plus k sigma. And this is for any random variable. The statement is for any, so that means this is the event. What is the event here? For all the sample points is corresponding random variable value. Okay, because random variable assigns values to, let's say, the sample points. Okay, and random variable, the sample point itself could be real numbers. Okay, then the question will be in that case, what are those numbers, okay, which are lying between this and this? And so probability of that, that means what is if it is a continuous curve, a continuous random variable, then what is the area? How can we estimate this area? And this theorem says this area, the probability of this, it at least this 1 minus k. So how much you are scaling, depending on that, where k is any positive real number, So that means without computing anything, this theorem for any random variable gives you an idea about the probability of an event. What is the event here? If you know the mean and the standard deviation or the variance, you can compute the standard deviation. So pictorially, if you want to look at this, so this is this x-axis, y-axis, there is some kind of, let's say, some kind of fx. I do not know, I mean, whatever it could be. Okay, let's say it goes to 0 here. And suppose somehow the mean is here. Okay, let's say it is the mean. Okay, this need not be, but let us assume that this is the mean. Okay, then you take this part, let's say this is mu minus some k sigma, some values of k you consider, and this is, let's say, mu plus k sigma. Then what is the area under this curve for the continuous case at least? So you can see this pictorial, you can visualize this thing. So, and this says it is at least, depending on the value of k, it is at least 1 minus k square. So without computing anything, just by using this formula, you can compute and estimate for some probability values. For example, I mean, there could be a problem like this. Suppose the PDF is given to you. So fx is given to you. Okay, somehow fx is given to you. And then the question is like the following. Calculate probability of mod of x minus some value. Let's some 3 less than or equal to some 5. It is given. It is asked. Then your guess would be whether 3 is mu for this PDF or not, and whether this, and then this, if you can find the mu and the variance or the standard deviation, then you can write this in this form, that x lying between this mu plus k sigma for some k, and mu minus, this is mu minus and this is mu plus k sigma, and then using this in this Chebyshev inequality, at least you can make an estimate that the least value, this possible value, is this. Whatever, 1 by k square for the values of k. Okay. This is an important thing. And another important thing is like calculating moments, meaning what? You have to perform a lot of integrations. So let's say you want to compute x to the power n. So you want to compute moments about the origin for different values of n. So for each value of n, then you have to compute this value to get an idea. What is the first order moment value, second order moment value, third order moment value. Even for discrete case, you have to take different sums. Let's say x1 square plus dot 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 plus xn square. Okay. If it is all are equally likely, then this is n, or then you have to take let's say cube of this, and again you have to perform a sum and so on. Okay, so this is a repetitive process. Sometimes it will be difficult also to compute each time this integration. So then a generalized idea of this is what is called the moment generating function. Okay, moment generating function. Okay, or this is called MGF. What is that? So this is an idea. This is kind of a function from which you can compute all the values of the moments just by performing a derivative of this function. Okay, all these values can be computed. In fact, moment generating function is defined as this. So let's say you have a random variable definition. Let's say you have a random variable x and you have the corresponding PDF of x. Okay, then the MGF. Then let's say a function m, because it is a moment, so I'm writing m. M is a function from R to R, defined as, let's say, mt is equal to expected value of e to the power tx. So x was the random variable with PDF. Now I'm creating a new random variable, which is e to the power tx. That means if it is discrete, so for x, let's say I have this x1, x2, dot 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 xn. Now for this e to the power tx, I will have for a fixed t, I'll have the value e to the power tx1, e to the power tx2, dot 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 e to the power txn. So basically what is happening, so whatever the value here, the x had, so I am taking exponential of that multiplied by t for any fixed t. Okay, so this is called the moment generating function if, of course, this expected value exists. Okay, if it exists for all t, okay, in at least an interval, let's say minus h less than t less than h. So from minus h to h, so in this interval, at least for some values of t, if it exists for all values of t inside, let's say this interval, for some interval, then we will say that this is the moment generating function of this. And next day we'll compute this moment generating function and we'll show if it exists, then you can, so let me write it down. So mt then will be this, sum over e to the power tx fx, where x is rx, this is for discrete, and for continuous it is minus infinity to infinity e to the power tx fx dx when x is continuous. Okay, and this could be just a homework, you can also find it out, maybe we'll prove it next day. Okay, that mth derivative, so if you take the nth derivative at this, which is, let me denote this, so that means d dt to the power n mt, nth these are this, and if you compute at the value t equal to 0, okay, this will give you nth order moment or nth moment. We'll prove this, but this is one way to compute all possible moments. And if you know all possible moments, you can compute, of course, expectation, variance, and many other things. So if somehow you have an access to guess a moment generating function of some random variable, you get a lot of information about the random variable. So all the information embedded here regarding expectation, variance, and other parameters, whatever you can define. So that are hidden inside this variable, inside this function, and you can compute those just by computing a derivative of it. Okay. Yeah, I think yeah. So I could not finish. I could not give you an example, but you can create an example like X. We have some PDF fx, and then you can compute mt using this formula, and then you can have. Then you can compute the derivative, and you can have all these values for different values of n. You will have nth order moment or nth moment. Yeah. So your exam is on, next Tuesday. So before that, there is a class on Monday. So I'll try to give you some examples, okay, regarding NGF. Yeah. If you have any questions, you can ask me. So that question, I can spend time right now. But if you have other question, you can tell me.